Hello, we are Team 1, and today we'll be discussing how we built our automated bridge inspection robot that is controlled by Arduino and Raspberry Pi microcontrollers. To provide background, we were contracted with building a robot to locate, mark, and temporarily patch bridge damage. To test our prototype, we will be detecting at most 4 fender washers on a 7 by 7 foot square whiteboard with surrounding walls, and then deploying a patch on each washer, all within a 75-second trial. We subdivided our task into subprocesses and utilized threading to run each process simultaneously. The utilization of global variables allows for each subprocess to essentially talk to each other. Raspberry Pi is used to control the vision system, location system, and patching mechanisms, while Arduino is used to control the wheel motors. Now we'll explain each of the main tasks of our robot. First, how our robot determines its location on the 7 by 7 board. In order to determine the location of the car at all times, we place an ultrasonic sensor on each side of the car. The distances of all 4 sensors and the current car orientation can determine the exact square location that the car and washer are currently in. Northeast-southwest correlates to each wall of the 7 by 7 foot square board. Therefore, each ultrasonic sensor is assigned to track the distance away from each wall. Since our car is constrained to travel in a straight line and only make 90-degree turns, we can keep track of all the 4 different orientations that the car will be positioned in throughout the entire trial. These orientations are denoted by 4 configurations. When the car turns, it changes to another configuration, as well as rotating the northwest-southeast wall assignments accordingly for each sensor. Once we have proceeded with the computer vision-based path planning and get the readings from the sensors, we send the motor commands from Raspberry Pi to Arduino through serial communication. Then the Arduino board pairs the motor control state, including forward, backward, turning left, turning right, and stopping. The motor control system uses PID control to enable the robot to drive straight or to turn at a specific angle. The PID controller uses the readings of left and right motor encoders as reference and the difference between the 2 encoder readings as the error. Our vision system consists of 2 pan and tilt servo motors, a Raspberry Pi camera, and OpenCV's blob and canny edge detectors. This combination of blob detector and edge detector allows to distinguish the washers from the white background and the patches. The blob detector also returns the X and Y coordinates of the detected washer that are later used for the servo pan and tilting tracking method. This tracking method uses PID controller to adjust the pan and tilt servos simultaneously so the detected washer stays centered in the camera screen while the car continues to move. With the continuous rotation of the camera, the car can see approximately 4.8 square feet of the board without even moving. This optimizes the path needed for the car to drive in order to search the entire board, as well as decreases the speed needed to travel 1 foot to about 1 second maximum. In order to keep the car on this projected clockwise path, the DC wheel motors rotate between being controlled by 2 different navigation modes. The ultrasonic-only navigation is the mode when the washer has not been detected. The motor commands are 100% controlled by the distance readings of the 4 ultrasonic sensors. Once the sensor reads too close to a wall, it commands the car to turn accordingly. The servo navigation mode is when a washer has been detected. The motor commands are controlled by the ultrasonic sensor's distance and the pan and tilt servo angles. The pan servo reads plus or negative 90 degrees. The car is told to turn 90 degrees in the direction of the servo. This aligns the washer with the front sensor of the car. When the tilt servo reads 45 degrees towards the ground, it means the washer is now in range of the patch being deployed. The patch will be manufactured by laser cutting slots into cardboard in the shown pattern to make the cardboard flexible. The patch will be placed on a spring-loaded platform that would raise the patches every time a patch is deployed. The patch is deployed from the top with the servo. A rubberized arm would be attached to the servo to push the patches. The patch deployment system will be activated every time the car is stopped and the detected washer is running from the vehicle.